Okay, let's look at global climate change, section 9.5. All the doom and gloom. Okay, let's review what the difference is between climate and weather. So weather is what you can see outside your window. It's in the now. And climate is a big, long average and what we expect. So the joke is climate is what you expect and weather is what you get. And remember from the beginning of the year, these climate grams or climate graphs, they're a big deal. So remember, you need to know which one has the look of the rainforest and of the tundra and of a temperate forest and a desert. So remember that little review should be coming your way. Okay, so how do we know that the world is getting hotter? So here's some indications. So anything with an up arrow, we're increasing. So increase in the air temperature, increase in humidity, temperature over the oceans, the sea surface temperature, the sea level is increasing, the ocean heat content is increasing, temperature on the land increasing, decreasing or less glaciers, less snow cover, and less sea ice. So all the things that are decreasing are things that have high albedo, how reflective a surface is to reflect heat back into the atmosphere and space. And if we're having things decrease, we're going to get a lower albedo and more absorption of heat and higher temperatures. Increase those temperatures. So those are some indications that the world is getting warmer. Okay, another big indication is this graph. And so we have looked at the average temperatures in certain places over time. The famous one is Greenland. And so you can see that there was a big increase and then it's kind of had these different changes, but lately we've really increased quite a bit. So this begins with shifting temperatures. We do have warming periods and cooling periods. You can see it goes up, it goes down, it goes up, it goes down. And all this data comes from these ice cores, and it's important that you know what an ice core is. So we've got these ice cores that are taken out of, you guessed it, ice. And so you can do that in Greenland or anywhere that there's a permanent ice located. And what happens is we have, the deeper it is, the older it is, and you can look at these air bubbles that got trapped with the ice, and you can analyze the air and see what's in there, how much carbon dioxide's in there, and how much methane is in there, and any other molecule that got trapped within those ice cores. So here's recent, and here's really old, and you can see how it changed over time, and then you can develop these graphs and see what's going on. So this famous one is the Vostok ice core, and you can see there are big shifts. It goes increases, it decreases, and lately, or to present, it's really risen. So there's a famous graph called the hockey puck, and so we have like this graph, and we have just kind of like increased, and it looks like a hockey stick. And the concern is that we have more carbon dioxide than we have had in the past. Okay, so these are the actual ice cores. This is where they store them. They freeze them in cold storage, and you can watch a video about it if you want to. I'll include the link down below. And they kind of talk about how they look at it. We might do it in class if we have time. So what is in this ice core data? So here's a cool infographic, and it can show you information. This one goes as early as 1750, and then it shows you recently we're getting to that dangerous 400 part per million, which a lot of scientists think is like the point of no return of when it's too late to go back. But there's weird things in here like, hey, look, here's 1975 and we can see DDT in here, and you can see lead falling in the Antarctic from the leaded gas. And so there's a lot of interesting little things you can look at on the timeline of the ice core. Kind of cool. Okay, so another thing is sea ice. So remember, sea ice is the ice that's on the ocean, and sheet ice is the ice that is on the land. Sea ice will melt with increasing temperature, obviously, The important thing with the sea ice is it protects all the life below it. It kind of traps the heat in and keeps the ocean warmer than it would be without that sea ice there. Water absorbs heat, it's dark, and then remember, light would reflect heat. So this ice on the sea has kind of a double job. It can reflect the heat above the albedo, and it can trap the heat inside already in the ocean to keep the temperatures a little warmer for the animals inside or underneath there. Big reminder again, sea ice does not contribute to sea level rising. So if I have a glass of water and I stick an ice cube in it, when that ice cube melts, the water level does not rise up significantly. So it's tiny, 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 insignificant. Okay, so here's another graph that we've looked at. So here's the atmospheric CO2, and we really never went above 300 parts per million until the 50s, and now we're rising, 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 and as of the day I recorded this, we are at 421 parts per million. So it's going up, and that's a concern to people. There's arguments that it's just part of the natural fluctuation that we see in the past, and there's arguments that nope, this is definitely man's fault and it's a big deal. There's some people that say it's only 400 parts per million, it's less than a percent, it's like 0.03%, why should we care? There's other people saying, well, now that we know about it, we should do something about it because we are responsible people. So you can take a side and do what you think is right for your moral code. Okay, here's some more evidence that the climate is indeed changing, because there used to be climate deniers. I don't think there's too many left that are going to deny that the climate is indeed changing. One of these big pieces of evidence is how far birds are flying south for the winter. They used to go quite a distance to go to warmer temperatures, and now they're not flying as far because they don't need to. The temperature's warm enough without flying so far. I mean, why would you go extra far if you're warm enough when you get there? So many bird species are spending their winters further north. Now think about that. That's going to affect the food web. There's a lot of things that depend on these birds coming when they come seasonally. And if it's not happening, it's going to have a big global effect on migration routes and other things. Okay, I love this video. Let's see if I can get it to come up. And it just
Hi,
shows
this is Bill Putman.
the breathing earth.
I'm a climate scientist at NASA's Goddard Space Flight Center. What you're looking
So we're looking at these carbon dioxide levels in the Earth's atmosphere, and it goes by time, and it just helps you see how the carbon dioxide levels change with season and by year and by greenhouse gas um, emitted by human activity. So some of this is fossil fuel combustion, and some of this is natural. But it's very interesting, I think, to watch it change. And so here's kind of it going quickly. So this is year by year. No, it's not. It's day by day. Anyway, I think it's kind of interesting to watch. Maybe it's just mesmerizing to me. And this is the year 2006. So you can see, like, even within the year, sorry, I stopped it too soon. Even within the year, it changes. So, like, this is in the winter, and that changes compared to how it looks in the summer. Here's summer. Anyway, I thought it was kind of cool. Okay, so carbon dioxide shifts with the seasons. Photosynthesis shifts by the seasons, and so it's very temperature sensitive. So plankton in the ocean will do photosynthesis at a different rate depending on the temperature. So summer rates versus winter rates are very different, and that can affect carbon production and carbon absorption. So remember that. Okay, so these graphs are showing greenhouse gases. So NO2 seems to be increasing. I would say the trend is increasing. Methane looks like that trend is increasing. Sulfur dioxide emissions increase. They've kind of a little bit decreased, maybe. I don't know. So then these are the CFCs. Those have gone down, with the exception of this guy. Male's kind of going down. It's starting to go down, but they stay up longer than the other ones. So all the things that cause climate change or global warming, those things seem to have been increasing. So duh. There is an international panel on climate change, IPCC. They issue a annual report on the condition of the climate. Some of it's hard to read, but some of it's not. And so it's human caused stuff, what's causing the disruptions, and what is happening ecologically, economically, and socially because of the disruption. So that's an interesting little read if you're super interested in it. It's also a career, unless if you're interested in it. So what happens with climate change? What are the effects? So obviously we get rising temperatures. The permafrost starts to melt. The sea ice starts to melt. Sea level starts to rise, and coastal populations have to move and get displaced. Marine ecosystems, I mean, in one way it's a good thing because there's more water, so they're going to have these new habitats, and that can be a good thing for if you're a marine life aquatic animal. But on the downside, there's going to be deeper water communities, and they're not going to be in the photic zone, the zone that gets the sunlight, because it'll be too deep because it'll have this sea level rise. And so fish that are used to be in the sun's photic zone may be too deep, and they have to rise up, and there might be some competition happening there. All right, another contributor to climate change is waste heat. Waste heat is like it sounds. We're doing something with technology, and we're burning something, we're using something. You touch your phone, it's hot. Well, that heat's going into the atmosphere. You touch a car that's been on, that heat's going into the atmosphere. That's waste heat. It's heat going into the atmosphere that's not really doing anything useful. So this low quality form of energy, waste heat, goes into the atmosphere and contributes to warming the, the climate. You can't change low quality heat to high quality heat. That's the second law of thermodynamics, or entropy. So we need to create more efficient appliances, create things that work without giving all this excess heat, this waste heat off. Um, One idea is the concept of cogeneration. Cogeneration makes us use waste heat so it's not so wasteful. So maybe you can use the wasteful heat to heat a home or to heat a space or heat our school or whatever it is, but we've got this energy in and we've got this work out, and hopefully we can um, cool off the waste heat for another use before we let it go into the atmosphere or into the water. Okay, so what's going on? Look at this picture. This is big time flooding. So when temperatures rise, coastal flooding, here it is, could be a consequence. Habitats are going to be underwater. So if you are a land plant and you are now underwater, you're not going to suddenly adapt to living underwater. You're going to die. If your roots are flooded, you need air for that and they're not getting it. It's going to kill off terrestrial or land plants and animals. So land plants or animals are probably going to die or relocate. All right, people get displaced. I don't think people are going to want to live here, so they're going to have to move. That's going to be an economic consequence. No one's going to buy that house, so how are you going to afford to get a new house if yours is flooded and drowned? Same with animals and plants. They're going to displace or die. The coral can become bleached because of all the pollutants in the flooding or the changes in temperature. And breeding grounds. So a lot of fish like to breed in like the seagrass area or the coral reef area, and it's near light. And if more water occurs, then the sunlight's not going to penetrate as deep, and that's not going to be a breeding ground anymore. So things will change or not happen as they used to, and it might take some time to adjust, or maybe they won't adjust at all and they'll just become extinct. Another thing that can happen with temperature change, climate change, is wind. Wind is driven by convection. Warm air rises, cool air sinks, and this circulation distributes the heat across our planet. It also distributes the water cycle and the moisture across our planet. If everything is warmer, there's going to be a slowing of convection or a stopping of convection. If there's not a difference in temperature, nothing's going to move. And these Hadley cells and the jet stream that are really important for moving moisture and mixing air will stop. And so we're going to have extreme hot areas and extreme cold areas and not so much just right areas. So we're not going to have this mixing of water. We're not going to have this mixing of air. It's going to be stagnant, and we're going to have some pretty major consequences, which are probably going to affect those keystone species first, and that range of tolerance is going to come into play in a lot of ways for a lot of different species. And it will ultimately affect us because the food web will be disrupted. Okay, ocean currents, same thing. The ocean's a great big conveyor belt run by also convection. So it's got cold currents and warm currents moving and switching. The big Arctic current is cold, cold, cold until it comes up here to the equator where it warms, and it gets less salty when it's up higher and more salty when it's down low. And really, this entire current spreads over the whole world and distributes heat across the ocean. So if we have warmer temperatures, we'll have less ocean current movement. That conveyor belt will slow or stop, and heat again will not be distributed evenly across our planet. That's going to affect upwelling, and remember, upwelling brings nutrients from the bottom up to the top for the fish, and if they don't get that, they're going to die. So remember, upwelling was associated with El Nino, but it could be associated with this climate change as well. So ocean water also influences the air temperature and the humidity levels, and that too, if it slows down or stops, could affect the entire climate of the world, and it could create droughts or floods depending on where that's happening. All right, climate can affect the soil too. Remember our soil unit? And the O and the A and the B and the E and the, is it C and the R, the parent rock and all of that. So anyways, the higher the temperature, the more evaporation happens. And that means water is going to leave the soil, and it's going to make it drier and making it more susceptible to wind erosion. And it's going to cause desertification. Remember that word. When it loses about 10% of its moisture. Okay, warmer temperatures are also going to release carbon dioxide gas into the atmosphere instead of storing it in the soil. So remember, warmer things store way less carbon dioxide than cooler things. Look at the differences in these arrows. More carbon dioxide released, the warmer the temperature. The decomposers get really active in warmer temperatures. So they're going to start sending more carbon into the atmosphere because they're going to activate and start decomposing things quicker. Loss of water means more erosion and loss of nutrients. So that's what's going to happen to the soils, which is going to affect economically, our food, environmentally, human health. All that's going to get affected because we're not going to be able to have the food that we need. There's going to be a food shortage. What? All these things. Now, remember that climate change can be a drought or a flood. So if it's high temperatures, we're going to get all those problems. But if it's a lot of rain and we get a bunch of floods, we also can have a bunch of erosion, more too wet of soil, losing the topsoil from runoff, and diffusing pollution of surface things. So if it's too dry or if it's too wet, we can have issues with our soil. We need just right. That was all from our agricultural unit, so you should remember that. Okay, so polar response. When the sea ice melts, it's going to expose this dark, heat absorbent open ocean. So the ice is going to reflect heat, but the ocean is going to absorb the heat. So when we lose the sea ice, the albedo is going to decrease. So we're going to absorb more heat. It's not going to reflect. So we're going to increase regional heat absorption, which is going to increase melting, because if it's hotter, it's going to melt more. And if it melts more, we're going to lose more ice and more albedo. And then that's going to make us get even warmer. And then we're going to get this warmer climate worldwide. So that is a positive feedback loop. So remember, it's a bad thing. We have this heating, the ice melts, and then we get lower surface reflection, so there's more heat. We get warmer ocean layer, larger things, and so higher temperatures again. It just cycles around in this positive feedback loop. We also get more biological activity in the ocean. We're going to get more radiation, more clouds, more vapor, more aerosols. All this stuff adds to it, and it's this really awful positive feedback group. Okay, now remember one last thing in the Arctic area. These animals have adapted to hunting on the ice for their food. So if this ice goes away, these animals don't know how to hunt without the ice. So that's going to be an environmental effect as well. Okay, so that is our issues with climate change, and hopefully that'll give you a little more insight of some stuff to put onto your FRQ.